Now let's understand a bit more about the system and the working. Now, what do you expect to happen if I keep on increasing intensity of this monochromatic source? We know intensity is directly proportional to amplitude square. So what we observe is, as we increase intensity of the source of light, current, photoelectric current also increases. So with intensity, what we find, there's a linear relationship of photoelectric current, and it is directly proportional. Alright, so that's what we observe. So what is the expectation if we increase voltage across the emitter and collector plate via variable potential source? We would find the graph over here. As we increase collector plate potential, we would find the photoelectric current also would keep on increasing. So if we increase the potential across E and C, we would observe that photoelectric current would keep on increasing. Alright, increasing, we know current is what? Rate of flow of charge. So it would be moving in with greater velocity, more kinetic energy. Alright, okay. Now, would the photoelectric current keep on increasing with collector plate potential, with increment of this potential? No. A saturation point would reach, and after that there won't be any, it would reach to an equilibrium and there won't be further increase in photoelectric current. Alright, then yet another interesting thing that is observed is, as soon as the photon strikes the metal plate, it emits electron without any time lag. Alright, so its emission is instantaneous, and approximately within 10 raised to minus 9 seconds the electrons are emitted. And again, as soon as we stop this, instantly the emission also stops. Alright, now let's get back to the same story again. So monochromatic source striking, electron coming out and getting collected on collector plate, keeps on collecting, keeps on collecting. It reaches its saturation level and there's no further increment in current. That's what we observe over here in our emitter. Now once this happens, what do? We make use of commutator. Now by commutator, what we do is we change the terminality. Now this becomes anode and this becomes cathode. So now what happens is, now this electrons are all deposited here. So now these electrons start moving towards anode. Alright. So what we do is, we with help of variable potential source keep on increasing the potential across this. So as we keep on increasing potential across this, we would find that the electron would be moving there at a particular potential. We keep on increasing potential, so we would be measuring some current flowing in, but at a particular potential we would find that electrons would not pass through this or would not record any current. Alright, so what do you understand by that? That potential is known as stopping potential. At that potential, the electrons are not able to cross it. So that itself means the energy possessed by this electron is related to stopping potential. Alright, so we can develop a relationship of kinetic energy, that is half mv square, where here v is the velocity of electrons and volt. The relationship is half mv square is equal to EV. Okay, let's understand the derivation part. Just to recap, kinetic energy max is equal to EV0 is equal to half mv square, which we had already seen. Here we had increased the potential, okay, and a particular potential we found that there was no current generated. So that itself means that the entire electrons, all the electrons were stopped by that potential. So we call that potential as stopping potential, and owing to which we got KE and we called it as max because that was the maximum velocity by which the electrons were moving. So it was Ke max is equal to EV0. This V0 was the stopping potential that we had applied, and which was equal to half mv square, and this velocity of electron which was there, we called it as V max. All right, V0 stopping potential already mentioned. E is charge of electron, which we know 1.6 into 10 raised to minus 19 coulombs, and C is, which we would be coming across, is equal to 3 into 10 raised to 8 meters per second. Formula we already had derived here, which was h nu is equal to h nu 0 plus Ke max. H nu is the photon provided by the source, and h nu 0 was the threshold energy required for electron to be emitted. So this threshold frequency was consumed from the h nu part which was provided by the source. All right, so and plus it was also utilized for the velocity of electrons, so kinetic energy. So h nu is equal to h nu 0 plus kinetic energy. All right, now kinetic energy is EV0. So h nu is equal to h nu 0 plus EV0. This is frequency and this is volt, stopping potential. All right, so we know that we can write this as this. So h nu is equal to same thing has been written here. Now if we want to find in terms of stopping potential, what do? We keep stopping potential here and we take this on the other side, forming h nu minus work function. All right, so E comes below, so charge of electron comes below. So if we modify it further, if we split it out further, what we get is hc over lambda E. So we know that nu is equal to c over lambda. So h is Planck's constant, c is velocity of light, this is wavelength, this is charge of electron, minus work function over electron, because we have just split it up. So this becomes our formula for finding stopping potential in any numerical. So these are few of the things that I needed to make you understand about photoelectric emission. All right, and let's try out some numericals now to understand it better.